All right, welcome. Today, we're going to crack open a really fundamental idea in math: how to take super simple, basic functions and turn them into these incredibly powerful tools that can pretty much describe anything you see. So think about it like this. You start with a basic shape, right? Like a simple U-shaped parabola. But how do you take that and stretch it, or squeeze it, or flip it upside down, and move it around so it perfectly matches, say, the arc of a basketball shot? Well, the secret is actually a set of just four simple changes. We call them transformations. And once you get these down, you can shift, stretch, and reflect any graph with amazing precision. It's kind of like having a universal remote control for functions.
Okay, so here's our game plan. We'll start with why these transformations are so powerful. Then we're going to split this up into two parts: the outside story, which is all about vertical changes, and then the inside story for the horizontal ones. After that, we'll put it all together, and by the end, trust me, you'll have a new graphing superpower.
First up, the outside story. Now, these are the changes that happen outside of the function's main parentheses. And the best part about them? They are completely intuitive. They do exactly what they look like they're going to do. It's great. Let's start with just moving the graph. If you add a number, let's call it d, to the whole function, the graph just slides straight up. If you subtract d, it slides straight down. Plus is up, minus is down. It's as simple as that. No tricks. So this number d is our control for the vertical position. It literally just picks up the entire graph, doesn't change the shape at all, and just moves it up or down the y-axis. Okay, what about multiplication? Well, when you multiply the whole function by a number, we'll call it a. You're either stretching it or squishing it vertically. So if a is a big number, like 5, the graph gets 5 times taller. If a is a small fraction, like 1/2, it gets compressed to half its height. And if a is negative, oh, that's easy. It just flips the entire thing upside down across the x-axis. So this a value is our vertical stretch factor. It's like the volume knob for how tall or short our graph is. And remember, all this stuff is happening outside the parentheses, and it all makes perfect logical sense. Okay, you ready? Let's move to the inside story. These are the changes happening inside the function's parentheses. And this is where things get a little weird, because what happens on the inside is almost always the exact opposite of what your intuition tells you. You know, what's really cool is that the source material for this actually calls this out. It says right here, this is the opposite of what most people think at first. So if this next part feels a little backward to you, you're not going crazy. It's a super common hurdle, and we're going to jump over it right now. Okay, horizontal shifts. When you see x minus c inside the parentheses, your brain screams, move left, right? But nope, it actually moves the graph to the right. And when you see x plus c, it moves to the left. It's always the opposite of the sign you see. So why on earth does it do that? Well, think of it this way. The change is happening to the x value before the function even gets to do its thing. To get the same output from f of x minus 2 that you used to get at x equals 0, you now have to plug in an x value of 2. So your x values have to get bigger to counteract that minus 2, which shifts the whole graph to the right. This same weird backward logic applies to stretching side to side. If you multiply x by a number b that's bigger than 1, like f of 2x, it doesn't stretch the graph horizontally. It compresses it. It squishes it by a factor of 1 over b. So multiplying by 2 actually squishes it by half. And yeah, multiplying by a fraction stretches it out. It's a reciprocal effect. And a negative b, that'll flip it sideways across the y-axis. Again, it's all about what the x values have to do to compensate. In f of 2x, your x values only have to be half as big to get the same result as they did in the original f of x. This is what causes that horizontal squishing effect. The key thing to burn into your brain is, for horizontal stretches, it's always the reciprocal, 1 over b. So we have our 4 moves, 2 easy ones on the outside, 2 kind of weird ones on the inside. So now for the fun part. What happens when you get a function that's got all of them happening at once? Okay, pay attention, because this right here is the most important trick in the book. When you have both a horizontal stretch and a shift happening at the same time, you must factor the inside first. If you don't, I guarantee you will get the horizontal shift wrong. You've got to pull that b value out to see what the true shift really is. Let's break this beast of a function down. We'll start with the easy part, the outside story. That minus 3 up front,
That tells us to flip the graph over the x-axis and stretch it vertically by 3. That +1 at the very end, that just means shift the whole thing up 1 unit. Easy enough. Now for the inside stuff. And what's our rule? We have to factor first. So we pull out that -0.5, and what's left inside is x plus 2. And now it's clear. The -0.5 flips the graph across the y-axis, and it stretches it horizontally by a factor of 2, because 1 divided by 0.5 is 2. And that plus 2 inside, that means we shift the whole thing left 2 units. Done. And this is basically the whole thing in a nutshell. This is your cheat sheet. Everything happening outside the parentheses is vertical and does exactly what you'd think. Everything inside is horizontal and does the opposite, working with reciprocals and opposite signs. If you can remember this chart, you're golden. And just like that, by mastering these 4 transformations and that one crucial factoring step, you've honestly gained a mathematical superpower. You're not just looking at graphs anymore. You can actually see the story of how they were built. Look, if you forget everything else from today, just remember this one core rule. Outside changes do what they look like they should do. Inside changes do the opposite. Just burn that into your brain and transformations will never trip you up again.
So, I'll leave you with a final thought. Just look around you. Think about the path of a baseball, the curve of a satellite dish, the rolling shape of a hill. Now that you know how to take any basic function and shift it, stretch it, and flip it any way you want, what kind of real-world curves could you start to describe with math? Think about it. Thanks for tuning in.